Okay, welcome to video 4 in this course, ST3 and probability. Here we're going to talk about basic Bayesian probability. So for those of you with some background in the history of statistics, you'll know that we typically apply frequentist approaches, which looks at the probability of some result, say a result X, given a particular model that's being used. It might be, for example, a linear model, and a hypothesis being tested. So you might have a hypothesis, alternative hypothesis, and a null hypothesis, and that might be that y can be dependent on x plus some sort of constant c in our linear model, and therefore that a x and y are dependent on each other in some form. Bayesian approach is slightly different. It looks at the probability of data, typically denoted d, given a model, given the evidence so far. So this maybe is our prior probability, and this probability that is inferred is the posterior probability. And what we add into here is the likelihood of the model given the data so far. So that kind of gives us some context for how likely our result is so far based on evidence. So this kind of gives us good, if we're looking at iterative approaches where we're able to sample repeatedly new data to add into our model, that can be more effective than the frequentist approach in certain situations. If we're sampling once, so we simply have input and a result for a test of some form, a frequentist approach may be the only possible approach. That a Bayesian approach may not be possible, but Bayesian approaches can be effective where we have repeated and comparable samples. So we also know the frequentist data is repeated samples from an overall population. Whereas Bayesian data is going to be sort of continuous data. In addition, the Bayesian approach starts with a prior that is updated by new data, whereas this new data is called a likelihood, and this generates a new posterior probability. So our likelihood could be something like this image, and our prior might be something like this, a smiley face. And therefore we combine the prior and the likelihood to form some sort of posterior probability that we can think about that combines our probabilities. And therefore, once we get new data, we can iteratively improve that as we go along. So what we consider with Bayesian approaches is that they're different than frequentist approaches because they assume that the parameters are constant during the processes, whereas Bayesian parameters may not need to be known specifically. They can be probabilistic, or indeed we can estimate the features associated with a parameter that is not yet specifically known within a process. Typically with frequentist approaches, we're looking at fixing parameters to estimate a statistic, whereas with Bayesian approaches, we're trying to fix the data to estimate the chance of a model. And therefore, you may be comparing between different models to see which one is most likely given the data we have so far, and that data might change. We also know that we have Bayes' rule that we mentioned before. So you can think about the chance of A if B has already happened. And this can be denoted as A given B as probability of B given A is probability of A given B by the probability of B itself occurring divided by the probability of A. So remember that you've got the numerators written here with the vertical bar, and then A is the denominator. So we can think about instances where A given B is the probability of A if A and B are independent. But here with this, we're assuming that some sort of dependence between A and B. So we're thinking about this outcome, that the probability of A and B together is the probability of A by the probability of B given A. What we can do there is sum across the options for B. So this might represent one option, B, one particular option, say roll of a dice. So that's not one. And we might have another one, B2, where we're rolling a 2 in a dice, and B3 might be, for example, rolling a 3. So when we think about this, we can imagine if that we had some sort of probability of a model given the data, we write as probability of data given the model, or the probability of data given the parameter or the model. So when you think about this, that we're looking at this intersection of BI across all A. The probability of all the options of B intersecting with A by the probability of A. So look at the probability of a particular event occurring, which is here, divided by all the different options on the denominator here. So we can think about this in simple terms. We could have a football match, and we look at the probability that's a nil draw as the denominator. And you have to bear with, my pen is very slow right now. So nil is our particular event, and we divide it by all the other possible events as the denominator. So when you simplify that, all the possible events will sum to 1. So that's going to be the probability of the nil draw alone for that particular event. But we make it more complex, so we might know that the game is a 1-0 team, and then we're going to work out the probability. What's the probability then of having a draw given this prior situation? So we can make things more advanced as we go along. We also have an example here from Lego. So we can imagine that we have 6 Lego blocks here. So we see across the x-axis, we have 6 blocks, and y-axis, we have 6 blocks as well. We have here a bunch of gray blocks. So we got 4 by 6, we have 24 blocks. Then we've got 2 by 3, so we've got 6 green blocks, and we have black blocks here, 2 by 6, we've got 12. So we've got green intersecting with gray and black, and therefore we might think, what's the probability of gray and green, or black and green, for example. So we can apply our Bayesian logic to this. So here we have the sum of all these is 42. When you link them all together, it's 36 blocks with 6 overlapping. And then we think about what's the probability of green given gray and green given that we have black already. So we can apply our Bayesian rule to this. So if we look at the black area, we've got 12 points in total here, 4 shades of green. So the probability of green given black is going to be 1 in 3. And if we reverse it, we can use Bayes' rule to work that out. So the probability of black given green is going to be the probability of green given black, which we have already, 1/3 by the probability of having black divided by the probability of having green. So that's 1/3 that's known. Then the probability of having a black square here is going to be high. It's going to be any one of these squares being black is going to be 1/3 from our model, because we got 12 black from 36 in total. And the probability of green is going to be 6 out of 36. So that's the denominator. So then we can work these out to determine what's the probability. So probability of black given that we have green is going to be 2/3, and that corresponds to the numbers we had. 4, if you recall, that we had 4 of the squares of the green squares were on the black, and then 2 were on the gray area. So you see that here, probability of black given the green is just the 4 black points on the 6 green, which is obvious when you outline it in this way. But we may not have this diagram available, and therefore we can calculate this out. So our likelihood is probability of green given that we have black. Another example of this is something you might have encountered already. So these classical probability questions, we might have probability of having a type of infection in a farm is 0.03. So we can write that down. Probability of infection is 0.03, and therefore the probability of not being infected is going to be 0.97. The test for infection is 99% accurate if the cow has the infection. So probability we test positive given that we have the infection is going to be 0.99. Probability of negative if not the infection is going to be 0.98. So then we can use these values to tackle the question. And what we want to think about is what's the probability of having the infection if the result is positive, and therefore we can use this here. So that's going to be positive given that it's infected by the probability of infection, which is 0.03 divided by the probability of having a positive test. So therefore we have some of these data already. We have 0.03 by 0.99 divided by the probability of a positive test. And we know that for a positive test, we just need to sum across the different options that we have. Present positive, given that you're infected, is one option, and that's going to be multiplied by the probability of being infected in the first place. And then we have the chance of being positive, given that you're not infective, multiplied by the probability of not being effective. Sorry, this should be I here. So we work this out. That's 0.99 by 0.03 plus 0.02 by 0.97. If we work this out, then this is about 0.049, which we can then put up to replace this value here. And therefore we can get an outcome. This works out at about 0.605 altogether. And you can see then, if we change the frequency of the infection, we just need to change these values. If we change the accuracy again, we just need to change these values. So again, we can change this. So we had a probability of infection is the same probability of positive if infected is going to 0.9 now. Probability of positive if not infected is going to be 0.05. I hope I wrote that the wrong way around, the right way around the first time. What's the probability of a cow having the infection if the result is positive? Again, that's going to be positive. Probability of being positive given the infected by the probability of being positive divided by the probability of probability of being positive, which is 0.9 by 0.03 divided by the probability of being positive. And as before, the probability of being positive is equal to the probability of being positive given that you're infected by the probability of infection plus the probability of being positive if you're not infected by the probability of being not infected, which is going to be 0.9 by 0.03 plus 0.05 by 0.97, which works out at, if I can read, about 0.01, which we can therefore put in here. Therefore, that works out at about 0.5 or 50%. So you can see how we change if we lower the accuracy values. That means the chance of our test being more effective in terms of the chance of infection if we test positive has now fallen. If we look at another example, you got a 99% of reliability. So that means the probability of being infected, the probability of being positive if you're infected is 0.99, and the probability of positive if you're not infected is 0.01. And we know the probability of infection is going to be 0.01. In the same as before, probability of being infected if you test positive is going to be the probability of testing positive if you're infected by the probability of being infected divided by the probability of being positive, which is 0.99 by 0.01 divided by the probability of being positive. Probability of positive comes from this above. So you have 0.99 by 0.01 plus probability of being positive if you test negative, 0.01 by the chance of being infected, 0.99, which works out as 0.01. If you put that up here, then that's about 50%. And just to outline that actually, I got the wrong values there. That's actually 0.076, and that percentage works out about 36% on the previous slide. I got the wrong calculations at the end, because that's for this question. If we then change the values, so we decrease the accuracy of the test at 90% and 90%, and we increase the frequency, so the probability of being infected now is 0.03, the probability of testing positive if you're infected is 0.9. The probability of testing positive if you're not infected is 0.1. That means our chance of testing positive is going to be 0.9 by 0.03 plus 0.1 by 0.97. So that comes from the number that are not infected up here. If we work that out, that's about 0.14. And that means the probability of being infected if we test positive is going to be equal to this 0.9 by 0.03 divided by 0.14. So you can work out the calculation yourself, what that works out as, but that might be, what would that be, of the order, let's say 0.3 or something like that. Another question is similarly, is you have two boxes. This contains 60 short bolts. So you've got 60 of them, 60 short and 40 long in the first box. The second box, we have 10 short, 20 long. You take a box at random and pick a bolt. What's the probability that you choose a short bolt? So what we need to do is look at the probability of choosing a short bolt, which depends on which box we choose. So for the first box, if we say the probability of choosing box 1 and box 2, so this is B1 and B2, we're going to add up the probability of short, given that we choose B1 based on the probability that we choose B1 in the first place, plus probability of short bolt, given that we choose B2 by the probability of choosing B2 itself. So in this case, this is a half and this is a half. So therefore, we can just look at the probability of choosing a short bolt given B1 and so on. So this is going to be 60 out of 100. And this one is going to be 10 out of 30. So we then work those out to see what we would get. So that's going to be 0.3 and 1/6. So it's about 0.47 altogether. So here we have the probability of A is 0.2, the probability of B is 0.8. Probability of being misfolded by A is going to be 0.01. Probability of being misfolded, given that as B, is 0.02. if we sample one misfolded protein, what's the chance that it's made by pathway A? So that's the probability that is made by A given that it's misfolded. So above, we're going to have that, it's going to be 0.01 there. We're going to have our next value is going to be the probability of is being misfolded divided by the probability, probability of A, and then probability of being misfolded. So we know that's 0.2 there, and therefore we have to work out what probability of being misfolded, which is the probability of being misfolded by A, by the probability of A, plus the probability of being misfolded by B, multiplied by the probability of B. So here, this first value is so yeah, we write it here, 0.01 by 0.2, plus the probability of 0.02 by the probability 0.8. So if we work this out, that's going to be 0.002 plus 0.016. So therefore, we get 0.018 there. And we can put that value in there for here, 0.018. And then if we work this out, we can figure out that this will work out as about 11%. And lastly, we can go to the final question, where we look at, and we'll do it with our code as well, where we look at the probability of being infected is 0.7, which means the probability of, that's I for infection, of not being infected is 0.3. So the probability of testing positive if you're infected is 0.9. Probability of testing positive if you're not infected is going to be 0.05. Therefore, we want to work out what's the probability of being infected if you test positive, which is going to be the probability of testing positive if you're infected, which we have here, by the probability of being infected, which we have here, by the probability of testing positive. So to get that, the probability of being positive, like we had before, is simply the probability of being positive given that you're infected by the probability of being infected plus the probability of being positive given that you're not infected by the probability of not being infected. So that works out as 0.9 by 0.7 plus 0.05 by 0.3. So if we work this out together, that's equal to 0.645. So therefore, these values are going to work out as 0.9 by 0.7 divided by 0.645, which gives us our outcome of 0.98 overall. So that concludes our video on applications of Bayesian probability. To introduce you to fundamental aspects of Bayesian probability, please see the subsequent videos for our video on applications of Bayesian probability.